Good morning, Kayim. Good morning, everyone.
Good morning.
Hope you're all doing fine. We have a few minutes left before starting. Thanks for sharing your screen and presentation. I propose to wait for a couple of minutes and then we can get the webinar started.
You can hear me. It's no problem for hearing me.
So, good morning, everyone. It's my pleasure today to introduce our two speakers, new speakers from the Netpore Coast Action. It's very, very enjoyable. This meeting we have once a month, discovering all the great research which is developed by all of you of interest, of course, in the Netpore Coast Action. So it's my pleasure to introduce Professor Kaying Wang today from the Department of Microsystem at the University of Southeastern Norway. Professor Kaying's research focuses on microfabrication and nanotechnology, electrochemistry, photochemistry, mainly for application in environment and energy. And today, Professor Kaying will be talking about micro and nanostructured silicon materials for solar energy conversion. Please, Kaying.
All right. Yes, thank you very much for Netpore organizer give me the opportunity for me to present our research at this platform. My name is Kaying Wang. I'm coming from Department of Microsystem, University of Southeastern Norway. Today, my presentation title is Micro-Nano Structured Silicon Materials for Solar Energy Conversion. Majorly, I will talk about black silicon fabrication and their applications. Go to the next slide. First, I would like to introduce myself, or my research, and our university. University of Southeastern Norway is a very new university in Norway. It has about 18,000 students and about 2,000 or 3,000 faculty members, located in 8 different campuses. I am working at Westford campus. The location is about south of the big city, Oslo, about 200 kilometers away from Oslo in the south. And the university was established in 2018. And our department of microsystem was established from year 2002 at Westfield Research Park. I'm working in this building. My research work consists of two parts. One is education, and another is for my research. The education part majorly on micro nano fabrication technology for MEMS, sensors and actuators fabrication and application. Majorly, this work are performed in our clean room. This is our clean room in map, and it is located at the second floor at here. This clean room consists of four we call the finger sections. Each finger sections has different functions. For example, for our micro and nano fabrication technology, for example, deposition, photolithography, packaging, and assembling, all we use different space for different applications, MEMS applications. And the second is my role is working for research is renewable energy. Renewable energy, I'm working on CO2 conversion, H2 generation, and supercapacitors, majorly through electrochemistry technology, working with nano materials or function nano materials. This is regarding myself and the university. I joined the university in 2007 and was promoted as professor in 2010. Then from there, I worked in this university for almost 15 years. My research work here is one of my research work. Today, I want to talk is on silicon material. Silicon material, we know that silicon is the second most common element in the Earth's crust. The concentration is about 30%, around 30%. It is based on silicon oxide, it's a compound. But for modern microelectronics system or MEMS system or MEMS sensors or actuators, they are majorly made from crystal silicon, because the crystal silicon itself have a property, physical, chemical, and mechanical properties. It has proper band gap, and the major property is isotropic micro machine. So this property allowed us to make a device. So when we process this crystal silicon, or we call silicon substrate or silicon wafers, we say they will show some black color when we process them. Like they always show residuals or byproduct on the silicon machining surface. We called it black silicon. And it was studied by people in 90s when people used microprocess called RAI microfabrication, reactive ion etching process. And then they found a large amount black colors on machined or micro machined single crystal surface. Later, another group, I remember it was in Harvard University, they also found similar properties when they processed silicon surface by using laser beam energy process silicon surface. They also found the surface was blacked by the processing. And the reason is because the silicon substrate shows nano structures, because these nano structures, they are when the incoming light radiate on the surface of processed silicon surface, or we call it black silicon. No light can reflect back. All of these young incoming lights was trapped on the surface. Currently, after people have long time study, nowadays we know black silicon surface, actually the surface showed nanostructures. Those structures majorly are nanopoles or nanowire, nanocones, or they also showed tailored structures. Based on the black silicon, people have done a lot of research. For example, they use this black silicon for solar cells or for thermoelectric conversion, or use it for night vision sensors, or use the night vision cameras, silicon-based. Generally speaking, currently in the market, this night vision sensor is based on MEMS-based sensor, or camera is based on magnesium oxide. Currently in the market, several groups, they are working use the black silicon for possible IR detection or camera applications. And for shall I continue? I hear some voice, some voice.
Yeah. Yes, sorry about that. Could you please turn your microphone off? Well, we don't hear. Just,
Yeah.
Kay, would you mind just have full screen of your presentation?
Yes,
Maybe?
yes, yeah.
Okay, that's
Shall
a
I, yeah, I hear the voice. Shall I continue or I?
Yeah, please continue. Sorry about
Okay.
that.
Yeah. I was thinking you may have some other arrangement, so I will continue. Regarding this other application, for example, drug treatment and chemical sensors, I know some of us from Netpore platform, some of researchers using a polysilicon. Here, I didn't see that the polysilicon. I only concentrate on black silicon. This black silicon, they also can be used for the drug treatment and the chemical-based biosensors. For myself, at Westford, at the University of Southeastern Norway, I used those black silicon majorly on photocatalysis application, and also use it for steam generation. Use it as a heat source for steam. Use the solar energy, convert into thermal energy, and then produce steam. And here you can see the left hand, I have black silicon. It was prepared by dry etching method. Use our method, I make a black silicon. Most of the time, this black silicon, when people use it, it can be active or passive substrate for different applications. If I separate those black silicon from different kind of setting in different classification, normally the black silicon can be nanopore, nanocone, or nanopellets. If we really want improve their light trapping properties, increase those light absorption, then people use different ways to do it. This is the general ways to do it. For example, use doping or grow a second structure on top of black silicon, use ALD or use CVD, or even use sputtering, this PVD method to load additional materials and then increase the light absorption. Whether it is photoelectric conversion or photothermal application, all of these two applications, they are based on the light trapping. So the first important thing is we increase light trapping, but for single fabrication method, general people get a single nano structure or micro structure. either get nanostructure or microstructure. Generally, now people use several ways to machine silicon. For example, I summarize here, people use 3 ways to machine silicon or make structures of silicon. One is called dry etching. Use dry etching, we use SF6 or use C4F8 or use O2, these gases to process silicon. Another way, it was started by those Harvard people. They use laser and then they still use SF6, use SO2 for etching silicon to make black silicon or nanostructured silicon surface. Definitely, this is the third group is very common. People use a white etching method. For example, use HF, H2O2, or KOH to etch in silicon to build up that when people use these 3 methods, we either can use with a mask, use a mask to do the etching, or we don't need a mask. Generally speaking, if we use a mask, the purpose is to get a microstructure, order the microstructure. And if we use a maskless without a mask, most of the time, those structures are disordered nanostructure. For example, in this situation, we are thinking, hey, we want to increase silicon's light absorption properties, whether we can use macro and nano combined structure, put these 2 together, then we get a macro nano structure and then increase silicon's light traceability. This is our idea from very beginning. Then in the later, we tried 2 different ways to do it. One, for example, we use 2 steps, called 2 steps, use dry etching and then dry etching. First, we use dry etching to make macro holes with mask. Then we use nano to decorate with nanostructures on the microstructure. We get macro nano structure silicon. Here I showed here is the Bosch process. This Bosch process is a very typical traditional MEMS process method. Normally, people use SF6, C4F8 in a plasma chamber. We can get a vertical walls into silicon. Most of the time, we use mask. We can get a microstructure. Then later, we use SF6, O2. We decorate with nanostructures on top. Definitely, we can also use white chemistry ways to make nanostructures on top of these microstructures. These are the 2 strategies we have used. And then here I showed the example, we just use 1 step, make nanostructured black silicon. This left hand is the parameters, SAP power, HF power, and pressure, oxygen, and SF6 flow rate. And the center here is the top view of nanoporous structure. Here is the tilt SEM image. We can see if we use 1 step, we can only get nanostructured. And then next few slides, I will show you several examples what we have made and their properties. One is honeycomb structured black silicon. It has a macro and nano structure. How did we make it? We use standard MEMS process. Silicon wafer, use photoresist, and then use mask. We open mask. Then we use the Bosch process, use the photoresist as a mask, make honeycomb structure. Then the last step, we use SF6 O2 process, get nanostructures on top of this honeycomb structure. Their properties I can show it here is, this is the SEM image. When we make a microstructure, we can see it have very good that array structure. Then we decorate with nanostructure. Here is the high magnification structure. Then later we cut it as small pieces and then load it on in a Teflon container for later property photothermal property measurement. Here is how did we optimize their property? How did we optimize the microstructures? Here show different regions. We design a different mask on a piece of wafer and then decorate with the same nanostructures. We can see whether we have nanostructures or macrostructures, they all have very good light absorption from 200 nanometer to 1000 nanometers. Only at in the infrared region, this macro and nanostructures absorption has some difference. For the thermal conversion properties, here I can show it clearly. First, we did the photothermal conversion experiment. We use this container, as I showed before. We put some water and then use a solar simulator, put it onto a balance. They measure the temperature and then measure the weight loss of water. Finally, we found that silicon with multiple or macro nanopores, they have very good light absorption properties because the temperature increased higher and then weight decreased fast. The yellow part is we also load with gold with a multiple scaled porosilicon. And then when we use a gold, it becomes even better. It has absorbed long wavelengths light from, for example, about 1000 nanometers. This is the first one. Second one, we did a similar measurement, use the photothermal electrical ways to measure it. We put a black silicon on a piece of thermal electric generator. Then we measured the voltage output. What we found? We found that multiple pole silicon with gold is the highest. But anyway, the silicon with the multi-scaled structure is also very high, higher than single nanostructure or microstructure. This is the conclusion. It looks like for us, we have a conclusion that micro nanostructure have higher absorption, higher capability to trap light than single macro or nano structure. This is the one structure. Second one is a structure. What we have made is a chimney-like black silicon. We change the macro structure. We machine the silicon into a chimney at a macro scale. Still use a typical photolithography and etching, and then finally we load with nanostructure and gold particles on chimney surface. What we found? We found the macro nanostructure itself, macro or nanostructure itself. They still shows the good absorption from UV to almost 1000 nanometers wavelengths. But all of them at higher, longer wavelengths, their absorption is not so good, Even though the macro nanostructure is better, but it's not good as we expect. We loaded the gold on top of it on the macro nanostructure. You can see from the right hand, we can see those absorption here is immediately absorbed, almost completely absorbed all the light wavelength from 200 to 2500. It's almost go to zero for reflection. It's immediately change the properties. And the gold particles could be found on the tips here, This is the second one. And the third one, we did another experiment, we made some nano wires. To make the nano wires, we use a different way to make it. We use gold particles as a mask. For example, we have used p-type silicon wafer, and then we deposit with gold, and then we have a heat treatment. We got this gold particle. Then we use Bosch process, use the SF6, C4ST8, and etch down. Finally, we use a gold etchant, remove those gold particles. This is the cross section and the top views SEM image. I will go to more interesting for hydrophobic or hydrophilic properties here. And then after we remove it, here this slide shows the spectral is similar without gold. Without gold, it shows at low wavelengths is similar as we expect, and high wavelengths is still the same as we expect. But this is a very good thing is regarding the water wettability properties. It showed super hydrophobicity. For example, I have a small video I can show you. The hydrophobicity is so high, and then we use a drop of water and a drop on the surface. It can be immediately bounce back, and multiple times it is still like a drop of water. Here you can see water going down, and then it's going back. And drop down and bounce back. I think I will stop here and go to next slide. Next slide is regarding what the machine we use. Actually, we use the machine, dry etching machine. It's called Plasma Pro 100 Estrella DRIE etching machine. This machine is available at our institute. Here is the process parameters, and then we can process different silicon, use a different chemical etchant, and then use different materials as a mask or materials we can. Here, what I showed here just show you we have the capability for all the Netpore members to let you know we have the capability to process different silicon or silicon oxide with black silicon or microstructured or nano-structured material. This is almost what I'm going to talk for today. Last, I gave a short summary. The summary at my group, I'm majorly working on MEMS-based sensors, UV or IR detection, and also use electrochemistry ways to make electrode for photochemistry or for water evaporation application. At the same time, I use electrochemistry ways to make titanium dioxide. All of this work have been done by my students. For example, currently I have several PhD students working with me and a postdoc with me, and also research work with me together. The funding are from EA and the Norwegian Research Council, even from the EU and the local funding. That's all from today. Thank you very much for your listening. Thank you.
Thank you very much, Ying. It was really, really interesting. Thanks a lot for this nice presentation. We have time for question. You can either start talking or raise your hand with your screen if you prefer. No question at the moment. I may have a couple. I think this water drop at the end is really, really nice. It's really fun. What did you,
Thank you.
How did you interpret this phenomenon? It's just because of highly hydrophobicity? That would be just the chemistry, or the topology plays an important role in this?
I think it's because the tension itself on the surface is different. It's not from just the chemistry. We get these hydrophobic properties. It really depends on their mechanical properties, not only just the chemistry parts.
All right, yeah. It's really cool. And talking about the double porosity system, where you have micron size pores and nano size, I was curious about the effect of the thickness of the nanopores that you have. Did you play with this thickness depending on how long you etch once you have, and how does it influence the reflectivity or the light absorption?
It's really a good question. It's really a good question. We played, for example, I know I was very fast on this slide. And then we played with the mask size. We use gold particles as a mask. And it really depends on the mask design. And then, for example, people can use a photoresist, or we use the gold as a mask. If the mask, when we use the Bosch process, you can see here, the slide here, when we etch down at the same time, it will etch side walls. It really depends on the mask we use here, nanoparticles, what is the shape and the design. And then when we etch down, we have to think about, we played these numbers. It can reach several microns, it should be no problems. If, for example, the scale here, I showed it's 5 micron, and it's almost kind of 5 micron or 10 micron, we can going down for nanowires. For nanowire, use the gold as a mask.
Okay, thank you. Thank you very much.
I have a question, Frederick.
Yes, please.
Yeah, thank you. Thank you, Professor Wang, for your presentation. I just, as a curiosity, you show some pictures, some images about random distribution of the pores and well-ordered pores or columns or pillars. So what is the best configuration in order to trap the light? So this random distribution or well-ordered, like you show here, very nice figures.
For us, with us, if you really want to have this this long wave, the full wavelengths, for example, from 200 to 2,500 nanometers, we need the structure with both plus gold. And if you really want this one, here for nano and for chimneys, for nano and macro, both are work, both are. For nano structure, even a little bit better. You can see a little bit better than macro. But when we let the macro structure going down, it shows the similar properties from UV to almost to IR. They are similar. It depends on that pillars, or you can chimney or those pillars design. This is a small those pillars design, like this honeycombs design. It's almost if it becomes smaller, close to the nano, then they show the similar properties. The only advantage, I think, is go to that that long wavelengths. We need a gold, loaded gold. Then otherwise, only macro and nano cannot extend to long wavelengths.
Thank you.
Mm-hmm. Thank you for your question.
Yes, please.
Hi, thanks for presentation. May I ask you a question? In the most beginning of your presentation, you have mentioned cone-like structures, not pillars, not chimneys, but cones. Do you produce cones? And if yes, could you shortly describe the process?
For the cones, definitely,
yeah,
thank you for the thank you very much for your question. It's really, I showed you for the cones, for example, for this structure, it's really, definitely for this structure, I have to say, it really depends on the mask design. You use the mask, and then the mask, for example, if you photoresist as a mask, and then if we design the mask with different thickness, we can get different top structures. When you design photoresist, this is a very tricky part. When you design the photoresist, either normally when people use photoresist, either is 1 and 0 you can either have photoresist and without photoresist, or another thing is we can design a gray mask with not so black and not completely. And then when you etch down, the mask itself also can be etched. For example, I said that the cone structure, you go to here, this slide. You can see here, the gold itself as a mask. Definitely at this structure, it also have etching at the side walls. So we need to think about when we do this etching, we really depend on the etching time, mask design, and those. As for example, if we want this another structure, SF6, or use a Bosch process, we're going down. The Bosch process, normally we have a small amount etching go to the side walls. Use both process, the macro process, the majorly we can get vertical wall. When we get at the beginning, I talk this, people play with different photorests and play with the number, this number, and this number. In my group, I didn't make this cone structure. Majorly on work on this and on this single nanopores and macro and nano structures. We also made some. We also made some chimney structures. I think we published in this journal. A few years ago by a PhD student.
Okay, thank you very much.
Thank you.
Thank you very much. Thank you, Professor Wang. Was very, very interesting. Let's speak now about present, and let me introduce you the next speaker of the day, who is Atis Duran. Atis here. I've seen her earlier today. She's currently an associate professor at Top University of Economics and Technology in Ankara, in the Department of Material Science and Nanotechnology Engineering. And Atis is also leading the Micro and Nano Interface Engineering Research Group currently. She actually has a very strong background in polymer engineering. And today she will present her research interest on the crystallization in nanopores, crystal growth, and polymorphism of confined polymers. Atis, it's yours.
Thank you very much, Frederick, for this nice introduction. Actually, my internet network is very unstable today. 2 times I had to reopen. In between, if I have such problem, I will try to enter with my phone. Okay, so today I'm going to talk about crystallization in nanopores, which is the heart, let's say, the core of my research activities, recent activities. Can you see the slides?
Yeah, just
very good.
Have it in a full screen eventually, please.
Actually, I thought I had a full screen. Let me try again. I will open here. Okay. Oops. Automatically, it's making like this. Let me.
That's perfect. Great.
It's okay?
Yeah.
Okay. So, well, I will start with first basic information about the crystallization, especially for the bulk crystallization. So the first part is like introduction of the crystallization. And then later I will share with you my research activities, especially focusing on the polymer crystallization in nanoporous aluminum oxides. Okay, well, as you know, crystallization is everywhere. If you look at the nature, the first, like for example, the one of the most common crystallization process is ice formation. Also in chemical industry, we use extensively crystallization process, for example, for isolation step of manufacturing many chemicals, and also for both particle formation and purification. As an example, I can give you the dyes, explosives, and photographic materials. They are like also based on crystallization. Again, in another industry, for example, in the pharmaceuticals, we use crystallization process because more than 90% of all pharmaceuticals contain bioactive drug substances and excipients in the solid crystalline state. And also in oil industry, well, in oil industry case, this is like an unwanted situation because the crystallization of hydrocarbon clathrates can clog the pipelines and can really cause some problems. So this should be controlled. Another example I can give from food industry, because this crystallization process is used for manufacturing like sugars, food additives, salts, and ice cream, and etc. We can give many examples. So, but in the crystallization case, we judge the quality of crystals based on the size, purity, morphology, and crystallization. But the first step in crystallization starts with nucleation. So that's why I will focus on the nucleations. And well, crystallization, as you see, can happen in different materials. I mean, ranging from metals to low molecular weight liquids, in ionic solids and polymers as well. Since polymers are my expertise, I will focus on only this type of material. So as you know, polymers are everywhere. And if you talk about applications, it ranges from the packaging to textile industry, laboratory equipments, household equipments to automotive parts. And the most common polymers are polyethylene, polypropylene, and these are actually mostly semi-crystalline polymers. So crystallinity control is very important, especially if you want to control their mechanical properties and also the optical properties. As an example, I will give you isotactic polypropylene bulk crystallization. Here you see optical microscope images of two common crystalline phases of isotactic polypropylene, monoclinic alpha phase and beta phase. Well, the crystallinity of isotactic polypropylene is in between high density polyethylene and low density polyethylene, so it is the range. But each crystal phase as a product behaves differently. For example, if you look at the monoclinic alpha phase, it has a higher stiffness and it is more sensitive to UV radiation, while trigonal beta phase has higher crystallization rate, superior toughness, and easier drawability. And also for the polymer case, the crystallization is very much depends on the thermal history and also thermal conditions and also processing history. So I will give brief introduction about history of nucleation theories. Actually, it has a long history and dates back to 1870s to Gibbs droplet model. Actually, the Gibbs droplet model is based on the phase transformation of fluid phase within another fluid phase, and he considers the minimum free energy with respect to radius of the droplets. But actually, we date the let's say classical nucleation theory based on Vollmer and Weber's model, and it's like dates around mid 20th century. Sorry, I need to close phone. Okay, so here it's based on thermodynamics, and before the crystal, let's say cluster name as a nuclei, there must be a critical radius, which is after that it's called nuclei, and it's based on this. And then later, Turnbull and Fisher develop extended crystallization classical nucleation theory for the crystallization from melt, and also Meyerson defined the crystallization from solution. But we know that actually all these models, pre-models, they make the crystallization two-step. First, the nuclear formation, and then the crystal growth. But we know that there are some experimental evidence as well, especially for the proteins. The nucleation has also two-step. And this is defined around 1997, Ishiyama and Tanaka, two-step crystallization. So now we have various extended versions of classical nucleation theory. We have also non-classical theories, because there are some defects in the classical nucleation theory, although we use this extensively. So let's look at what is the classical nucleation approach. Okay, let me first introduce the terminology. There are growth units. This can be an atom, this can be ion and molecule, depending on the materials. For example, for the metals, it's atom. For ionic solids, we use ions, and for the polymers, for example, growth unit is a macromolecule. So when these growth units collide and they form aggregates or clusters, when they reach a certain dimension, and above this dimension, we call them, this is actually critical size, we call this as a nuclei, okay? And classical nucleation approach is actually based on capillarity approximation. So capillarity approximation says that there is a interplay between the interfacial free energy, because once we go through phase transformation from the melt phase to the nuclei, we are creating a new interface. And also, since this is a phase transformation, there is also a difference in the free energy between liquid and crystal phase. So there is a balance between this. So classical nucleation approach is actually based on pure thermodynamics. So, and also, in order to nuclei form, we need a driving force, okay? And driving force can be, in case of crystallization from melt, is a supercooling. Supercooling means that this is the melting temperature of our crystal, our material. And when we cool this to a set temperature, this difference is called supercooling, okay? In case of crystallization from solution, then the driving force is the supersaturation. For example, when we prepare a saturated solution, and then when we cool this solution and we bring it to a metastable limit, there we create a concentration difference, and this is the driving force. So as I told you, this approach has two main concepts. One is that there must be a local density fluctuations. And then second one is the existence of large structural difference between the degree of order, whether it's in the melt or in the solution, and also the nuclei. But nucleation is a probabilistic phenomenon, and it implies using energy, creating a surface. If you look at, although classical nucleation theory is used extensively, it has a lot of weaknesses. And I will give you some, let's say, most important weaknesses. First of all, this theory assumes that it's based on assumption that the nuclei is in a droplet form, so it has a spherical shape and have uniform densities. But from experimental results, especially from atomic force microscopy results, we know that nuclei can have irregular shapes, like having facets or dendritic structures. So assuming that it's a spherical structure is not always correct. And second assumption is that the surface tension of liquid droplet is equal to the bulk surface tension. But we know that and in these small clusters, we have around 100 molecules. And we know that the surface tension changes with the droplet size. And this creates also Laplace pressure. And then this creates instability as well. So this assumption is not correct because the nuclei is actually in a nano size. And also this theory is based on, there is only criteria is whether an aggregate or cluster become a nuclei or not. So it's based on size, okay? But there must be also that there is a collisions between the growing units, also pre-existed clusters. There must be a break-off and of the pre-existing clusters and so on. So this has to be taken into account as well. Another assumption is that nucleation rate is time independent, and it's based on steady state kinetics. But we know that there is also certain time lag, and there is a transition time before the steady state situation exists. So these are the weaknesses. But I call nucleation theory as let's say, I like it because it can fit all types of materials, I mean, we can apply this to polymers, ceramics, and metals, but this is at the same time the weakness of the model, because there we know that the dynamics of these each growing units are different, and this has to be taken into account as well. But anyway, still we use this model extensively. So if you look at this model from the thermodynamics perspective, and the net free energy change from phase transformation from the melt state to the, let's say, nuclei formation has two parts. One is a volumetric contribution, another one is, since we are creating a new surface contribution. So, and the phase transformation is related with the chemical potential change, and since it's a volumetric process, and if we assume that the nuclei is a sphere, we use the volume of the sphere. But the creation of new surface is proportional to the surface free energy, and also is proportional to surface area. So then overall, if I plot this here, see, I get a barrier, and this barrier actually is a nucleation barrier. If I take the derivative of the Gibbs free energy as a function of the radius, then I can calculate the critical size where these growing aggregates can be stable and can be named as nuclei. So, well, I told you that then we need a driving force to have a nuclei, and one was the supercooling. But supercooling has to be also, we have to be careful with supercooling, because as the supercooling increases, the interfacial Gibbs free energy decreases, and also the free energy difference between liquid and crystal phase increases, as you can see. But also, as the supercooling increases, the kinetic factor, because in order to grow, the growth units should diffuse and join the aggregates, but the kinetically this is becoming harder, and kinetic factor decreases. So overall, when we look at the nucleation rate, as you can see, we have also a barrier and a maxima. So this has to be balanced as well. So actually, the model is based on, although homogeneous nucleation, it can be also heterogeneous nucleation, which means if in the melt or in the solution, if we have a foreign body, this can be a dust molecule, or this can be a catalyzed or foreign body, then these sites, if the molecule wets the foreign surface, it can crystallize on it. Okay, but here the important thing is wetting of the surface. And here I try to depict these growing units are riding on the heterogeneous surface, and they are forming aggregates, and above the critical size, they are forming a nuclei and also crystallizing. So the wettability is described with Young's Laplace equation. Here you can see interfacial energies, and cosine theta is actually a contact angle between the liquid phase on the substrate. And looking at this ratio, actually we can estimate whether homogeneous nucleation or heterogeneous nucleation is more favorable. For example, if the liquid wets the foreign body when the contact angle is approaching zero, then homogeneous nucleation is more dominating. While if the liquid doesn't wet, when it doesn't like the body, then this ratio gets higher, and then heterogeneous nucleation becomes more favorable. So if we plot free energy exchange as a function of nucleus size, as you can see, for example, here, black curve is for the homogeneous nucleation, and the red curve is for the heterogeneous nucleation. Energy barrier for heterogeneous nucleation is much smaller. Actually, most of the time, we are dealing for the bulk materials, and in the industry, in terms of application, we are dealing most of the time heterogeneous nucleation because energy barrier is much lower. So, well, then let's look at how this crystallization in bulk changes when we confine the materials inside spatial geometries. Confinement geometries varies. For example, It can be in the droplets, spherical shapes. It can be in ultra thin films, nano layers, and so on. Or even the block copolymers. So I divided confining geometries to 3 parts. One is one-dimensional, for example, cylindric nanopores can be a good example for that. Or if you make a multi-layers of films in food industry, we use this actually. As you can see, these are the many layers. And then this is a 2-dimensional confining. And then also the droplets, spheres, for example, mini emulsions. These are the 3-dimensional confining geometries. So for a long time in my research group, we were using nanoporous aluminum oxide membranes for different purposes. And then we decided to use work with only 1-dimensional confining for the investigating crystallization. Okay, here I summarize my research group activities. Actually, when I was doing my Marie Curie postdoc research activities at Max Planck Institute, I was trying to produce nanopillars on gold transducers because we were using surface plasmon-based biosensors, and we were trying to make these arrays of nanorods and then try to amplify our signal. And then when we were, let's say, characterizing our nanopillars, we realized that their crystallinity was very much different from the bulk crystal. And then we were also looking at the protein dynamics in the nanoporous aluminum oxide, and we were mostly interested in how the glass transition temperature of the proteins are changing in nanoconfinement. But then, for example, first polymer that we worked was polybenzyl L-glutamate, and then we realized that there was 50-degree shift in the melting temperature for the proteins, and this was like unusual to us. So when we were going in this direction, we ended up working with confines in the crystallization in confinement. So this was the beginning of our story. Okay, then, so this is my, let's say, main template for nano-confinement. This is the nanoporous aluminum oxide. The beauty of this porous membrane is that it has a very homogeneous distribution of the pore sizes. And also we can systematically change the sizes of the pores, ranging from 25 nanometers to 400 nanometers. So here you see electron microscopy images of our pores. These are like a top view, and this is the cross-sectional view. And for this case, actually, Martin Steinhardt, he is also a member of Netpore. He produces very nice, high-quality aluminum oxide membranes, and he was providing us. And then, so we start first with isotactic polypropylene. And these are the other polymers that we work. And here I want to take your attention to bulk crystal sizes. As you can see, they are huge, and they are forming these 3-dimensional spherolytic structures. For example, for the IPP, normally when there is no restriction in the bulk phase, the spherulites after impeachment, they have as big as 10 micrometers in diameter crystals. Polycaprolactam, we work with various molecular weights, but the size of the crystal changes from 20 to 50 micrometer. Polyethylene oxide changes from, let's say, even larger, it's a 300 micrometer. So let's begin with isotactic polypropylene. So as I told you, we put isotactic polypropylene in various sizes ranging from 25 till 400. So these are top view. We did extensive cleaning because we don't want a surface crystallization. We just want to see how nanorestriction affects their crystal behavior. So this is our DSC thermograms, and the black curve is for the bulk IPP. As you can see, bulk IPP has a melting temperature around 110 degrees Celsius. And in this graph, S stands for excess film, where we couldn't remove. I mean, because there is always, no matter how much you clean, some excess polymer left on the surface. And E stands for heterogeneous crystals, and O stands for homogeneous crystallization. What I want to say is that when we systematically reduce the size of the pores, what we observe is that we were eliminating heterogeneous crystallization while we were getting low temperature crystals, which are named homogeneous crystals, because there is a very large saturation. Initially, we didn't understand whether this was homogeneous crystallization or not, because before us, there was one group reported that it was published in PRL in 2007. They were observing differently, because when their pore size, and they use also nanoporous aluminum oxide for the polyethylene, they were observing that for the pore sizes smaller than 40 nanometer, they were observing heterogeneous crystals, while when the pore size was higher than 60 nanometer, they were observing homogeneous crystallization. It was just opposite. So then we said, is this a universal effect? And we want to search in deep, and what is the reason for the homogeneous nucleation? Because if you look at the 25 nanometer ones, we don't have any more heterogeneous nuclei, but we have only homogeneous nucleation. So first we correlate this with, we compare the volume of the nuclei with the volume of the pores to see if it's really special restrictions. So, for example, we know the bulk volume of the spherulite, and it is around, let's say, 5 times 10 to minus 7 millimeter cube. We know volume of a 38 nanometer pore, which is in the order of 10 to 8 millimeter cube. The smallest pore size, 25, has the volume of 10 to 5 times 10 to 11. So, and the probability of nucleation, we realize that probability of nucleation depends on the volume, not the surface area, because when it's smaller, the surface area was getting. So what we did is that we calculated enthalpy of crystallization as a function of pore sizes, and we extrapolated this enthalpy to see the size where we don't have crystallization anymore. And from this extrapolation, we find that when the size of the pores are around 20, the polymer is not crystallizing anymore. And we checked this with the classical crystallization theory using the thermodynamic parameters. And from this theory, we estimated that when the size of the crystal is between nuclei between 10 to 12, it doesn't, I mean, this is the critical size. Below this size, it doesn't crystallize. So it's in the same order of magnitude, but surprisingly, for the same polymer, for IPP, and with the same molecular weight, we saw that in the literature around 2007, Zia's group, they did atomic force microscopy measurements on the nuclei size, and they find the critical nuclei size around 20 nanometers, so it really matches. We look at also crystal structure, whether if it is changing. What we see is that when the pore sizes are getting smaller, the high order crystal peaks are disappearing, and 25, we only see hollow amorphous phase. So below the 20, it doesn't crystallize anymore. So it's very much suppressed. So then, as I told you, we were curious to know if this is true for other polymers. We work with polyethylene oxide, another semi-crystalline polymer. And this time we change also molecular weight of the polyethylene oxide. And then, yes, we see that the same effect there. So the black curve is for the bulk crystal, and the other ones are for the nano-confined crystals ranging from 200 to 25, and we only see homogeneous crystallization. And similarly, when we compare the bulk nuclei size with the confinement size, we see that, okay, sorry, yeah, here, we see that, for example, classical nucleation theory states that the critical size for polyethylene oxide is around 1 to 10, which is smaller than isotopic polypropylene. So this size is, since this size is much smaller than the 25 nanometer, still the pores that 25 nanometer pores has still some degree of crystallization. So it is around 20% crystals. So when we look at the molecular weight dependence, we realize that it's also depending on molecular weight, because smaller molecular weight has feels the confinement more, and also molecular weight, since molecular weight affects the mobility and also diffusion of the macromolecule, and so this is also molecular weight dependent. So these curves, the spheres are for the low molecular weight polyethylene 1070, triangles are for the medium molecular weights like 2005, and then the rhombi is for the higher molecular weight, which is 8,200 rounds. Well, then we also check another very common industrially relevant polymer, semi-crystalline polymer, which is polycaprolactam. And for polycaprolactam, something interesting happened. What we observe is that we had extra heterogeneous nuclei. We call them surface nucleation because we know that in the pores, not only at the bottom of the pore, but also the pore walls are acting as nucleation sites. And to really check if this is for the surface, because inside the alumina membranes, because it is produced electrochemically, there are a lot of, let's say, anions residing, and these anions also contribute, it can also affect crystallization. So we try to neutralize the surface, so we cover it with the octodecylphosphonic acid. So once we cover it, we eliminated this extra heterogeneous nucleation sites, and we observed only homogeneous nucleation. In the literature, we saw that people observe similar behavior, and they call this fractional crystallization. So there are many fractions of different types of crystals, heterogeneous, several heterogeneous crystals, and also homogeneous crystals. Last topic, I am not sure if I have time. This confinement effect is worked with extensively with block copolymers, because in the block copolymers, when the melting temperature is very high, one crystalline block sees also confinement due to the existence of the other block. And this is the case, for example, for polyethylene block polycaprolactam. So because melting temperature of polyethylene is around 55 degrees Celsius, polycaprolactam is 65. So there is a 10-degree difference. Already, before putting in the nanopores, the polyethylene oxide feels the existence of polycaprolactam. So in this way, when we put them in the alumina, we see double confinement. The first one, we named this as soft confinement because of the block copolymers. And the second one is called hard confinement because of the rigid role of the alumina pores. So if you look at this is the block copolymer. When we change the ratio of polyethylene, the polycaprolactam, when we increase the percentage of polycaprolactam, polyethylene feels the confinement more, and then the melting temperature.
Tek birden almaya gerek var mı?
Sorry? The crystallization temperature of polyethylene is shifting towards lower temperature, so it is suppressed. But when we put in this block copolymer in the nanoporous alumina, we systematically observed changing from heterogeneous nucleation to homogeneous. But another effect we observe is that polyethylene oxide doesn't crystallize anymore, only polycaprolactam crystallized. We realize this after checking the wax pattern because it has a characteristic crystallization peak. And then, so when there is a double confinement, the one of the blocks doesn't crystallize at all. So we also checked the, let's say, dynamics of the blocks and using dielectric spectroscopy, but now I'm not going to into deep this. But what I want to show is this. When we plot the crystallization temperatures as a function of pore diameter, we realize that homogeneous nucleation, when the size gets smaller and smaller, the crystallization temperature in confinement is reaching the glass transition. For the heterogeneous nucleation is almost controlled by the melt temperature. So this was actually important observation that we realized. So that actually we realized that for the confined systems, we should investigate crystallization with the glass transition temperature. So in conclusion, I can say that confinement induces several characteristic features during the crystallization, and pore to spatial restrictions needs to be larger than the critical nucleation size. There is also compartmentalization effect because when we put in more compact geometries, we might eliminate also catalytic sites or foreign bodies. And there is also molecular weight dependence of the crystallization. And we know that molecular weight affects also glass transition temperature. So overall, it's safe to say when we spatially restrict the crystallization, homogeneous crystallization is more favorable than the heterogeneous nucleation. So this was a collaborative work between my group and also the Max Planck Institute led by Dr. Hans-Jürgen Butz. And also, of course, this actually was initiated, the first idea to study the crystallization in confinement by Dr. George Fludas at the University of Ionia. And then we did this using the Max Planck Gesellschaft at a partner group. I also thank them for the financial support. Well, we didn't only work with polymers, we work also like say liquid crystals, some like let's say even molten salts and also types of different materials. But of course, we had very limited time. I didn't put all the results, but I put the list of publications there. You can see effective confinement on their crystal behavior, also crystal structure. Thank you very much.
Thank you very much, Hatis, for this great presentation. It's very, very interesting, very informative, instructive. It's very, very nice presentation and work. Are there any questions for Hatis? It doesn't seem so. I may have a short question for you. So this system is very interesting for you to study the properties of nucleation in confined conditions. I was wondering if there is an interest in using then the polymer that you can grow into a nanostructure, to use it directly or to use it as a nano casting, for instance, by dissolving the template that you have used, or is it just a system to study the thermodynamic and nucleation properties?
You know, initially we were not interested with crystallization. I also found it at the beginning boring because crystallization is a very old topic. Well, we want to produce nanopillars, as I told you before, and then but we realized that crystal structure is changing, the crystallization temperature changing. It affects also the stability and also dimensional stability of the structures, nanostructures. So then now I separated my research into two categories. One is application of these crystalline structures. Another one is to see the fundamentals of the confined crystallization. Because there, for example, I know that we cannot apply anymore the classical nucleation theory. Maybe we need to develop a nanocrystallization theories. So this is another direction, like fundamental research. In terms of application, yes, because also, as I told you, crystal structure affects mechanical properties as well. One of the materials we work, I didn't put it here, but polycyanorates. For example, they have a lot of aromatic groups and they were aligned parallel to the four walls. And we realized that we measure these new crystal structures, structured nano rods, mechanical properties. The Young modulus of the single rod was 20 times higher than the bulk one. So this is really affecting. In terms of application, when it's stronger, maybe this will be better reinforcing agent in the composites, for example.
Okay, thank you very much. Thank you for all this explanation. Again, it was very interesting. Is there any question for Hatis before we close the session? We have a few seconds. Okay, so if not, we can thank our two speakers again today. We don't upload on Zoom, unfortunately, but thank you very much. Thank you to Professor Wang too, and I wish you a great day.
Thank you very much. Bye-bye.
Thank you, Hatis. Thank you all for participating to the webinars.
Bye-bye.
Bye-bye.
Bye, Louise.